Greetings, my dear students. So for this set of slides, we'll be talking about work. And this would be our second to the last application of the definite integral. So this would be one long video to listen to, recording to listen to. So make sure that you have a stomach full and you have a focused and mindful set of mind. That way you'll be able to grasp and understand and absorb everything that I'm going to discuss in here. So let me start with the fundamentals of this particular set of slides, what our guiding learning objectives. So at the end of this particular set of slides, you'll be able to calculate work by a variable force, calculate work done by springs, and calculate work done in pumping fluids. Okay, so these are our three guiding learning objectives. They are quite a challenge to listen to, but hopefully you'll be able to learn a lot from this set of slides. Now, if a constant force of magnitude F, so this is our representation of the force, is applied in the direction of the motion of an object, and if that object moves a distance d, then we define work W as the product of the force applied in the direction of the movement of the object. So work is equal to F times D. So in this case, this is our fundamental definition of work where the force being applied is constant. So take note that the motion of the object is in the same direction as the force that is being applied. So let's move on. So as an example of work being equal to the product of the force applied and the distance covered, or the distance of displacement of the object due to the application of the force, we have these two. So an object moves 5 feet along a line while subjected to a constant force of 100 pounds in its direction of motion. So we can say that the work done, W, is equal to the product of the F and the D. So F being the force, which is 100 pounds, and distance covered by the object, or the distance of displacement of the object in the direction of the force or of the motion, is 5 feet. So it's 5 in here. So if you multiply the two, you will have 500 foot pounds. Okay, pounds being the unit of our force. Now, some or in physics, since you're done with physics already, this pounds is in pound force, understood to be different than pound mass, because we have two units for pounds in English. One is pound mass and the other one is pound force. So in this particular application of the work, the 100 pounds is 100 pound force. Okay, let's have another application. This time it's in SI units. So an object moves 25 meters along a line while subjected to a constant force of 4 newtons in its direction of motion. So if you notice in this problem, it's always specified that the force is the same in direction to the motion or displacement of the object. So in both of these examples. So in the second example now, we have work done W being equal to the product again of the force and the displacement, and that would be 4 newtons for the force and 25 meters for the displacement, giving us a work done of 100 Newton meter, equivalent also to 100 joules. So these two examples of work being the product of the force and the displacement is the, shall we say, the common example we have for work wherein the force F is constant. Now, in the case of the application of the definite integral in determining work applied on a moving object, most of the time the force is a function of the displacement. So for you to understand that, let's move forward to the next slide. So let's go now to work done by a variable force applied in the direction of motion. Now suppose that an object moves in the positive direction along a coordinate line while subjected to a variable force. So take note This time, the force is variable. So meaning it's not constant. If you notice specifically, it's a function of x. Now, it's variable force that is applied in the direction of motion. Now, define what is meant by work W here, performed by the force on the object as the object moves from A, which is, let's say from X, which is A, to X, which is B, and find a formula for computing the work. So in our next discussions here in the succeeding slides, our force, this force here will be a function of the displacement x. How could that be, or what particular practical scenario can we use to illustrate that the force is a function of the displacement of the object, or the distance covered by the object in the same direction as the application of the force? Now, on the right-hand side here of our slide, you could see a spring. So if you want to pull the block attached to this spring, so this is our block horizontally, so we're going to move it in this direction. Our movement is in this direction. Then we would have to apply more and more force to the block to overcome the increasing force of the stretching spring. So as the stretching of the spring, or as the elongation of the spring increases, more force is needed for this block to be displaced farther away from where, from the rest position of the spring. Let's say, for example, this is the rest position. So this is an example wherein the force that you are applying is increasing because you are extending the spring. So the more or the longer the spring becomes, the greater is the force that you are applying. And as such, that's the essence and the significance of having to apply definite integral in determining work done by a variable force in the direction of motion. And that would be our main focus in the succeeding slides. So I will clear all markings here and we'll move on to the next slide. So the integral for work W with a variable force would then be represented by this particular formula. Suppose that an object moves in the positive direction along a coordinate line over the interval A to B, while subjected to a variable force f of x that is applied in the direction of motion. Then we define the work W performed by the force on the object to be equal to the integral of the function of x, or of the force, multiplied to dx, which is the displacement, integrated from A to B, because this is the interval to which your object is moving along in the positive direction in your coordinate axis. Now let's move on. Now let's have this first example. So a 60-meter climbing rope is hanging over the side of a tall cliff. So can you imagine that there's a cliff and this is a 60-meter climbing rope hanging on that side of the cliff? How much work is performed in pulling the rope up the top, or up to the top, where the rope has a mass of 66 grams per meter? The other requirement is how much work is performed pulling a 60-meter climbing rope up a cliff face where the rope has a mass of 66 grams per meter. If you look closely at the questions, they seem to be, shall we say, the same. In here, how much work is performed in pulling the rope up the top, or up to the top where the rope has a mass of 66 grams per meter. The other one, how much work is performed pulling a 60-meter climbing rope up a cliff where the rope has a mass of 66 grams per meter. Now, they may seem to be the same, but actually they're not. So to illustrate what I mean, let's say I'm not really good in drawing. So let's say this is your cliff. So this is our cliff. For example, let's say there's a tree here. So you can envision that this is the cliff. Now on this cliff, you have a rope. So I will color the rope this time red, so you would see. So you have this rope here hanging. Its length is 60 meters. So that's our rope hanging on the side of the cliff. Now this rope, this particular rope has a mass of 66 grams per meter. Now in letter A, what you're going to do is you're going to pull this rope up the cliff. So you pull it up here. Okay. In letter B, the entire rope will be carried to the top of the cliff or will be carried on top of the cliff. Not that it would be like pulled up like this, but like in our language, amat-amat. But uh, but in the second scenario, everything all at once, the 60-meter rope will be pulled up the cliff where the rope has this mass. So in the first scenario, if we will let X the amount of rope pulled in, so X is the amount of rope pulled in, meaning in letter A, you will have already some, say, I'll put a dash line here. Meaning this is the amount pulled in. And this is X. Then it follows that the remaining amount here will be 60 minus X because the entire rope is X. That is for letter A. You pull the rope slowly up the cliff. So in that case, if we want a force expression, the force will be from your physics. Force here is equal to the weight of the rope, which is its mass, times the gravitational constant. So in our expression here, the gravitational constant is 9.8. So this is our G. This 0.066 is your 66 grams converted to kilograms, because we know that if we have this G as 9.8 meters per second squared, your mass should be in kilogram. That way your force will be in newtons. That was discussed in physics. So this G, which is 9.8 meters per second, will be multiplied to the mass, which is 0.066 kilograms. Now we're good with that. This entire expression actually is your G and the mass, but the mass has to be multiplied still to the remaining part of the rope that is to be pulled in. So if you have pulled in already X up, then the remaining weight in which you're going to apply force on would be 60 minus X. So this is the entire expression for the force that is being applied on the rope. The mass, which is this one. This is your entire mass. Why? Because the mass that is given to you is per meter length of rope that is to be pulled up the cliff. So if the rope is 60 meters long and you have already pulled up X, then the remaining to be pulled up is 60 minus X, and that would be the weight that you will pull up, or that's the equivalent force that you will apply for the weight that you will apply to the weight of the rope that is to be pulled up. So this is the G and this is the mass. So the entire expression is the force. Now with this entire expression as the force, what would be the displacement? The displacement is dx, because if this is x, the length of the rope as it is being pulled up the cliff, then the displacement of the rope at any particular time would be dx. So the rope is being displaced from its original point here by this differential dx. So that's your displacement. So this is your formula. This is the d in your formula for the work, which is force times d. Now, since your displacement is the distance in which your rope will be displaced from upon the application of this force, your limit of integration will also be that length of the rope. It will have to start with zero distance here, and going up until the entire rope is already up the edge of the cliff. So that would be until 60. So this is an example of a work wherein the force is the function of the displacement itself, and this is the displacement. So by comparison, you could see we can consider the work done in lifting the entire rope 60 meters. The weight of the ropes is 60 times 0.066 times 9.8. And this is the entire force that you will apply, because at one time only in letter B, all of this rope, you can probably think of it or assume that it's being rolled up. The 60-meter rope is rolled up, and then all at once it will be pulled up from a 60-meter distance. So this is the total weight of your rope, the 60 times the 0.066, which is the 66 grams convert to kilograms. So this is your mass, and this is the G. So in this case, your force is constant in the second scenario. And you will apply this force for 60 meters, because we assume also that your cliff is as, or your rope is as high as the cliff. So whatever is the length of the rope, that would be also the height of the cliff. So the force here is 60, the displacement, times the force applied. So that would be giving you 2,328.48 joules. So the work applied in lifting the entire 60-meter rope all at once, so the term here, entire 60-meter rope all at once, will be greater than pulling it up slowly, displacing it x from its original position. So this end of the rope will also be displaced by x, because whatever length here goes up, the same displacement you have here, meaning this is the 60 minus x that I have. That's the 60 minus x that you will apply to the mass. That way you will have the weight of the remaining rope that was not yet pulled up the cliff. So I will erase this part here, because this one is a much clearer representation of the x and the 60 minus x. So if you have a displacement from this part of x, that's also the length of the rope that has reached this part of the cliff. The remaining length will be the one that will be multiplied to this mass per unit length. That way you will have the total mass multiplied to the G, giving you the total weight of the rope, which will also correspond to the force that you will apply to it. So there's greater force, there's greater work done in lifting the 60-meter rope, the entire 60-meter rope up a 60-meter high cliff, rather than pulling it slowly up the cliff. Okay, so this is work in which the force being applied is variable. So let's clear our markings. Let's go to our next example. Now, consider again pulling a 60-meter rope up a cliff where the rope has a mass of 66 grams per meter. At what point is exactly half the work performed? So it's the same as this particular scenario in example 1. However, it's asking at what point or at what particular displacement from the original uh, location of the end of the rope was it lifted up high the cliff to reach half of the total work done. So from example 1, we know that the total work performed, so this is our total work performed, okay, by slowly pulling up our rope up the cliff. Now, we want to find a height such that the work in pulling the rope from that height of x equal to 0 to a height of x equal to h, which we want to know, is only half of this total work. So that would be 582.12, half the total work. Thus, we want to solve the equation like this. This 0.6468, where is it coming from? So remember, it's still displacement. Okay, let me have annotation here. So it's still displacement. This is your displacement, and this entire expression is your force. So your force is the mass of the rope times the corresponding length that is not yet pulled up the cliff times the corresponding distance in which that particular part or weight will be pulled up. Now, where is this particular expression coming from? It's actually taken from our uh, regional problem or regional sample problem, this one. So the expression for the force is exactly the same as the first expression we use for the answer of the first question here. And we just equated it to half of the total force. So if you do the maths, if you do the mathematics, this is your expression. You will have to distribute the 0.6468 to 60 minus x, and this will be your answer. And then after that, or rather this is not the answer, you just simply have to distribute. So distribute it and you will have to integrate. So the product of these two is a constant. So when you integrate, you have the x on it. The product of these two is 0.6468x, but it will be now processed using integral. So this will become x squared over 2. So that is why your 0.6468 here became 0.3234 because you divided by 2 already. So your integral, notice, will be evaluated from 0 displacement to h displacement. The height, the problem is asking for. The height or the displacement of the rope and from its original position when half of the work is done already. So if you do the maths again here, you substitute the h for the x. So you will have this as h and you will have this as h squared, and you have here a quadratic equation. So meaning you will have two possible answers. If you process it using quadratic equation, you will have h equal to 17.57 and the other one is 102.43. Now, it is in cases like this that there is a need for you to validate or really check your answer, whichever is applicable. Since we only have a 60-meter rope, you cannot lift it to the height of 102.43 because we assume that the displacement over rope end will be also equivalent to the length of the rope itself. It's just like your cliff is also 60-meter high. So you cannot have a displacement that is longer than the 60-meter rope. Even if, let's say, for example, we did not assume that our cliff is 60-meter high, you cannot have a displacement of the rope end from its original position, which is greater than the length of the rope itself. Let's say you did not assume that your cliff is also 60-meter high. So you cannot, it's impossible to have a displacement of 102.43 for the end of your, from one end of your rope, because your rope is only 60 meters long. So as the rope is only 60 meters long, the only sensible answer is this one. The H is 17.57 meters. Thus, about half the work is done in pulling up the first 17.57 meters. The rest of the 60-meter rope, which is 42.43 meters long, will require the other half. So there is much greater work applied in the first 17.57 meters up the rope, of the rope up the cliff, because there's a longer length of the rope on the cliff, on the base of the cliff, that was not yet pulled up, translating to a heavier weight. So that is why your 17.57 meters length will require half the rope. Then the other half will be requiring, other half of the work would be requiring to pull, will be required to be used to pull up the remaining 42.43 meters. Okay, so that's a continuation of our first sample. So let's clear the drawing and move on. Now in here, let's try a different example, different than the first one that we have. So it talks about the rope and the cliff. This time it talks about a box containing 100 pounds of sand. So this box is being pulled up at a uniform rate at a distance, so pulling up at a distance of 50 feet over 1 minute. Now the sand is leaking from the box at a rate of 1 pound per second. So as you're pulling this box up, this corresponding amount of mass of sand is leaking from the box. The box itself weighs 5 pounds and is pulled by the rope weighing 0.2 pound per foot. So there's a lot of things going on in this problem. You have a box weighing 5 pounds. It contains sand, rather, yeah, it contains sand, which is 100 pounds, but this sand is leaking from the box at a rate of 1 pound per second. And the box, as it is being pulled up, is pulled up by a rope weighing 0.2 pound per foot. Now, the distance in which this box is to be pulled up is 50 feet, and it will be pulled out at a rate of 1 minute. How much work is done in lifting just the rope? So quite similar to the first and the second sample problem. How much work is done lifting just the box and the sand? So box and sand, and what is the total work performed? Meaning all three now taken into consideration. The box, the sand, and the rope, all of which needs force to be applied to it and needs work for it to be pulled up. Okay, now we start by forming the force function. So we need to, very important, since this is a variable force work application, you need to set up correctly the force equation. So we start by forming the force function F sub r of x for the rope. So the subscript r here is for the rope, where the subscript denotes we are considering the rope. As in the previous example, let us denote the amount of rope in feet pulled in. Okay, let's denote it by X. Amount of rope pulled in feet, and the weight of the rope with X being the feet pulled in is, so you have this one, the weight of the rope or the mass of the rope per unit length. So that would be mass per unit length times the remaining part of the rope that was not pulled in. So if you have a, where is the 50? Okay, so we are to assume that this distance of 50 feet will also be the length of the rope attached to the box. So Whatever is the distance that will be traversed by the box in being pulled up, that would also be the length of the rope. So if you have already pulled up X length, then the remaining part of the rope that is not yet pulled up will require a certain amount of force, and that would be the 50 minus X. That will be multiplied to this one. So this is the length, mass, 0.2 pound per feet or foot, times the remaining length that was not pulled in. So the entire expression is 10 minus 0.2x. So that would be the force. So if this is the force, the 10 minus 0.2x, we need the displacement, which is the dx. And since we have a 50 feet distance, same also the length of the rope, then our integral will be integrated from 0 to 50, giving us the work required for the rope only to be pulled up equal to 250 foot-pound. So what you have to do here, class, is use power rule and then substitute the limits 0 to 50. Your calculators, by the way, can do it directly for you without not having to really illustrate the uh, shall we say, power rule technique of integration. So that's for the letter A. The work done lifting just the rope. So letter B would be a challenge because this time we'll be accounting for the work done in lifting the box together with the sun inside the box. So let's clear the markings here and let's proceed to the next slide. Now, the sun is leaving the box stated in the problem at 1 pound per second. As the vertical trip is to take 1 minute, then we know that a minute has 60 seconds. So meaning, let me annotate. It would take you 1 minute. It would take you 1 minute to pull the entire box with the sun up. So this 1 pound per second will be multiplied to 1 minute, where 1 minute is 60 seconds. So we cancel the minutes, we cancel the seconds. So that would be 60 pounds. Okay? 60 pounds of sand will be leaking from the box in the time duration of 1 minute, the same time in which your box with the sand will be completely pulled up. We know that 60 pounds will have left. So that's what I'm saying when the box reaches its final height of 50 feet. So again, letting X represent the height of the box, we have 2 points on the line that describes the weight of the box. When X is 0, meaning the box was not yet lifted, it was not yet moved from its original position, the sand in the box is 100 pounds because it did not yet leak, because it was not pulled up. So that would be producing a point which is 0, 100. It's one set of coordinate. So the first number is distance or displacement x. The second number is the amount of sand inside the box. Now, when X is 50, when your box is completely pulled up from its location, the sand in the box only weighs 40 pounds. Why 40 pounds? Because we have computed here that the 60 pounds will have leaked already. It would have leaked already in the duration of 1 minute, because it would take us 1 minute for the box containing the sand to be pulled up. So the remaining is 40. So when X is 50, the sand in the box rather will weigh 40. So this is another coordinate. It's just like the first number is X, the second number is Y. Now the slope of the line would be, of course, the difference in Y. So for 100 minus 40 divided by the difference in X. So 100 minus 40. This is not plus 400. Okay, this is only 40. So 100 minus 40 divided by 0 minus 50. So this should be negative. giving you an answer which is 60 over 40, which is negative 1.2. So this is correct. Giving the equation of the weight of the sand at height x as an expression like this. So it's like weight as a function of displacement. So since we already know the slope, then you can choose any of the set of coordinates. You will be getting this 100. What do you mean by that, Miss Ali? So for example, you have weight is equal to negative 1.2x. You do not know the y-intercept here. Isn't it that when we have the equation of the line, you have y, you have m here, you have x, and you have the y-intercept b. You already determine the slope of the line, which is negative 1.2. But you still do not know the y-intercept. So all you have to do is choose from any of these two sets of points. So if you choose displacement to be 0 and 100 for the sand weight, this one displacement is 0 and 100 for the sound weight. So you will have, I'll place here at 0 and 100. In this equation, you will have 100, the sand weight is equal to negative 1.2 times 0 plus b. That will be giving you a b, which is 100. So that is why this is the equation that is given here. The weight of the sand inside the box as a function of the displacement of the box. So the box itself weighs a constant 5 pounds. Remember, this is the weight of the sand. But the box only weighs 5 pounds, but it's a constant. So your total force will be the sum of this negative 1.2x plus 100 plus the 5. So that would be your expression here for the force. So negative 1.2x plus 105. This is the expression for the force needed to pull up the constant weight box and the variable weight sand inside the box, and this is the displacement. So the answer for letter B will be 3,750 foot-pound force when you already process this integral. Letter C asks for the total work. So the total work will be the sum of the work in pulling up the rope and the work in pulling up the box with the sun. So that would be the 250 answer in A and the 3,750 answer in B. That should give you 4,000 foot-pound force. So if you did the integration as a whole, meaning you did not separately solve A and B, then the expression for the rope force, which we had a while ago, and I'd like to go back to that. This is the expression for the force for the rope, 10 minus 0.2x. We add to that the expression for the force for the box and the sun, which is negative 1.2x plus 105. All will be displaced by a distance dx. Our integral will have a limit from 0 to 50. The answer would still be the same. So either you do separate computation for the work done in pulling up the rope and work done in pulling up the box with the sand, or you do it in just one computation like this, your answer would still be the same. In this scenario, the only part wherein we have applied the variable force work concept is in the case of determining the work done in pulling the rope and the work done in lifting the sand inside the box. The remaining sand inside the box that has not yet licked. Because in the case of the box, its weight is constant, so we did not use a variable or an expression of the force in terms of the displacement because the box is said to be weighing a constant weight of 5 pounds. Okay? So I hope you learned something more. You learned more from these three examples. Let me clear the markings here and let's proceed to the next. So this is our third example. So let's go now to the application of Hooke's law and spring work. So we are done with the first objective, work done by variable force. Now we go to determining the work done in elongating a spring, or we call it spring work. And we use together with it Hooke's law. Now, what is Hooke's law? So Hooke's law states that the force required to compress or stretch a spring x units from its natural unstretched length or compressed length is proportional to x. That is, this force is equal to f of x, which is equal to the product of k and x being the compressed or stretched part of the spring. Now, this K is what we call as the Hooke's law constant because this expression is Hooke's law. Now, for example, if a force of 1 Newton stretches a given spring 2 centimeters, so meaning this is the elongated length of the spring already or the change in the length of the spring, then a force of 5 Newtons will stretch the spring 10 centimeters. Now, how was this arrived at? So how was this particular, especially this statement here? Then a force of 5 Newtons will stretch the spring 10 centimeters. The first thing you do is you determine the Hooke's law constant because we're talking of the same spring here in the first set of data given. So the first data says that, by the way, if our force is equal to Kx, or Hooke's law, then here our set of data is 1 Newton, you have K, and your displacement is 0.02. So this here will, the first set of data will give you the value of the Hooke's law constant. So let's check the value of the Hooke's law. So the value of our Hooke's law constant in this case is 50. So as illustrated here. Okay, so if it's 50, given the same expression F is equal to Kx, then we can say that a force of 5 newtons, so if this is 5 newtons, will stretch the spring of length 10 centimeters. How did you know that this would be the displacement or the change in the length of the spring if you will increase the application of the force of 5 newtons? So you will only need to apply the K that you have solved here based on the first set of information. So you place here the 50 and that would be X. Now we have here X equal to, so your 5 divided by 50 would be 0.10, or that would be 1 over 10. Now, this 0.10 is in meters because this one was converted, take note, in meters. The 2 centimeters here I divided by 100 to convert that in meter. So that would be your 0.02. So this 0.10, if you multiply it by 100, would be the 10 centimeters that is being mentioned here. Okay? So you have that. Now, it's important that you know this concept. Anyway, this was explained, I'm sure, in your physics, that if we're talking about the same spring, the Hooke's law constant for that spring will not be changing. The reason why it's called a constant. So that will enable us to determine either the reduction or the increase in the length of the spring or the amount of force needed in elongating or compressing the spring, whichever of the two information is known and unknown. So meaning knowing F will solve the X if you know K. Or knowing X will solve the F if you know K. So it's just as simple as that. Okay? Now let's move on. Clear the drawings again. So example 4, we talk now about spring work. So a force of 20 pounds stretches a spring from a natural length, this is the unstretched length of 7 inches, to a length of 12 inches. So in here, we can say that so we'll annotate that the change in the length of the spring would be 5 inches. Now you're asked to how much work was performed in stretching the spring to its length. So in many ways, we are not at all concerned with the actual length of the spring. That's correct because we're only uh, concerned with its change or the change in the length of the spring. So only with the amount of its change. Hence, we do not care that 20 pounds of force stretches the spring to a length of 12 inches, but rather that a force of 20 pounds stretches the spring by 5 inches. So it's a different thing. We're not really concerned how much is the entire length after the application of 20 pounds, but what we are more concerned is the change in the length due to the application of the 20-pound force. So this is illustrated in the figure below. We only measure the change in the spring's length, not the overall length of the spring. So from this unstretched condition, now your spring was stretched up to this part due to the application of a 20-pound force. Okay? Now, clearing again, and we move to the next slide. Now, converting the units of length to feet, so we have the displacement already as, so let me annotate. Your delta x already, we have determined in the previous slide as 5 inches. We convert that in feet, so that would be 5 over 12. This is the displacement, right? So in our formula, in Hooke's law, this is the delta x and this is the k. And you have here the force, which was mentioned to be 20 pounds. So then that would give us a value of the rate constant or the Hooke's law constant, which is 48. Okay? Now, your expression then for the force as a function of the elongation or the compression of the spring or as a function of the change in the length of the spring is 48x. This is your K and this is your x. Now, this is a force expressed as a function of the change in the length of the spring. So it's just comparable to saying that a force expression which is also varying in terms of displacement or the change in the length of the spring. So when we want to know the work done in stretching the spring in this case, because from 7 the length was extended to 12, then that would require this expression F, this 48x which is F, and the displacement dx. Now, your limit for integration would be from 0, meaning this is not uh, the spring, let's say, is in the undisturbed position. It was not yet stretched to the change in the length. So 5 over 12 because 5 inches is the change in the length of the spring. So the rest is your mathematics giving us spring work, in this case, to be 4.1667 foot-pound force. So in spring work, what you need here, the work in spring work is the force from Hooke's law. So the force expression from Hooke's law and then the displacement. And then you just have to attach or you have to affix the correct limit of integration. So this is your delta x, the change in the uh, length of the spring. Okay? Wait. So our work in this case is f dx from 0 to delta x. Okay? That's how simple spring work is. Okay, clearing this again, we'll move to the next slide. Now, the most challenging part, so we have already accomplished first two objectives, work done by variable force, work done by spring, the work done in compressing or stretching a spring. What about work in pumping a fluid out of a top of a tank? Okay, you want to measure the work, how much work is required in pumping fluid from inside the tank to outside the tank but on the top part of the tank, meaning you don't have a faucet on the base of the tank, but rather the work would be in pumping up the fluid to the top of the tank. So another useful example of the application of integration to compute work comes in the pumping of fluids, often illustrated in the context of emptying a storage tank by pumping the fluid out the top. This situation is different than our previous examples, for the forces involved there are constant in the case of uh, uh, the work done by a variable force and the work done in compressing or stretching a spring. What is meant by this constant is it's a constant expression but not a constant number. And after all, the force required to move 1 cubic foot of water, about 62.4 pounds, is the same regardless of its location in the tank. What is variable is the distance that this cubic foot of water has to travel. So water closer to the top of the tank travels less distance than the water at the bottom of the tank. So we say that water in pumping, or rather work in pumping a water on the top of the tank will require lesser force than what pumping the water at the bottom of the tank, because the water this time will cover a larger distance.